To finish Unit 1 in our review of the basic algebra skills that you're going to need for this class, we're going to finish up with writing and solving inequalities. The big difference here being instead of dealing with equations and dealing with times where x equals something, we're going to have x in an inequality where it may be greater than or less than or greater than or equal to or less than or equal to some value. So instead of seeing an equal sign, we're going to see an inequality sign like the ones you see here. An inequality compares two unequal values using one of these symbols. And if you remember these from back in 802 class last year, you see a less than, you see a less than or equal to, a greater than, and a greater than or equal to. Remember from all the way back in 3rd or 4th grade, whenever it was that you saw these, the alligator opens up to the larger number, so you see that it's always going to open up to the bigger value, and that helps us read these correctly. And then remember the bar under the less than or the greater than sign means that the value could also be less than or equal to. So for example, if I had something like x is greater than or equal to 8, that means that x has to be greater than or equal to 8. That means it could be 9, 10, 11, any value that we know is larger than 8, but it could also be equal to 8 and still be true. That takes us into our idea of a solution. The solution of a variable of inequalities is the set of all numbers that produce true statements when substituted for the variable. Go back to that example of x is greater than or equal to 8. Any number of values can work for x in this case and still be true. We see that 10 is greater than or equal to 8. We see that 100 is greater than or equal to 8. And we could even go far as to say that 8 and 1,000 is also greater than or equal to 8. Because it's an equal sign, we could even say that 8 is greater than or equal to 8. So notice there's going to be a set of all numbers that work here. There's not going to be just one number that works. And to show this then, instead of just trying to list all these possibilities like I have here, we can use a number line, as you'll see. The one important thing that you need to remember from last year, anytime you multiply or divide each side of an inequality by a negative number, you must flip the inequality sign. Let's look at an example here. I have the inequality negative 3 is less than 5, and I think we all agree that negative 3 is smaller than 5. However, if I was to multiply each of these sides by a negative number, in this case negative 1, something interesting happens. Because we have a negative times a negative on the left, that becomes a positive. It becomes the opposite of negative 3, which is positive 3. Same thing happens on the right, which is now an opposite of 5, or negative 5. If I were to write the inequality as I've already seen it, we would have 3 is less than negative 5, and we know that's not true. In order to make sure our statement stays true, we must flip the sign. So that's any time we multiply or divide by a negative number. Other than that, your background knowledge will take care of the rest. Let's look at some examples. These are one-step inequalities that you see right here. Negative 7x is less than or equal to 35. From your background knowledge, you know you want to use inverse operations, and whatever you do to one side, you must do to the other side. But again, notice, because we've divided by a negative, that's going to make us have to do something with the arrow. X is now greater than or equal to a negative 5. Then it just is a matter of graphing all of those solutions. Think of all of those values where x is bigger or equal to negative 5. To show that, I want to find that boundary marker of negative 5 and mark it. There's two ways that we mark these, if you remember from last year. If x can be equal to that value, we use a closed dot. If x must be greater than or less than that value, we use an open dot. In this case, because we see that bar and we know that x can be greater than or equal to negative 5, we'll first start by marking that spot with a closed dot, because negative 5 actually would produce a true statement when substituted in for x. Now I'm looking for the values where x is greater than or equal to negative 5. When we think greater than, we think the values on the number line that are greater than that are to the right. That would be your answer, and that would be the set of solutions that would work for that particular inequality. Another basic example would be m plus 9 is less than 7. Again, your background knowledge takes care of the solving portion. This just means that we need to be able to graph this properly. Because we didn't multiply or divide by a negative, we leave our arrow. M is less than negative 2. First, we want to find that boundary. In this case, it's negative 2. Now, when I think to this, I wonder, can negative 2 work? Is negative 2 less than negative 2? I think we all agree that negative 2 equals negative 2, and so that would not be a possible solution. In this case, we use an open dot to show our value. It's up to and including, up to but not including that point. Now I'm looking for values to the left because they are less than negative 2. In this case, that would be our answer set as graphed on the number line. They won't all be this simple. We'll also have some multiple step equalities like the one you see here. But again, background knowledge is very valuable to you. If you follow the cover-up method, you know that you would subtract 5 on both sides first, and then to get x by itself, you would divide by 3. That gives you an inequality of x is less than 3. Picture graphing this. The first thing you want to do is find that boundary. In this case, it's 3. It would have to be an open dot because it does not include 3, and we would draw our arrow to the left because all numbers to the left of that spot would work and would be less than 3. The most difficult and possibly newer item for you to understand is the compound inequalities. Use your background knowledge and think of how to approach this. You're still going to use inverse operations, and you still, whatever you do to that variable side, you must do to every side. What you'll now notice is I don't just have one side, but I have two sides to this inequality that I'm going to have to keep track of besides just the variable term. To solve, I will look in this middle term and see that I have x minus 3. To get x by itself, I would add 3 just like always. But now I know I have to add 3 both to the right and to the left in order for this to work. I now have the inequality 1 is less than or equal to x, which is also less than 7. You'll notice these compound inequalities will have a very different look on their graph. Because they're bound on both sides, we won't have arrows going on in both directions forever. To help you graph this, I recommend separating this into two different inequalities. I have the inequality of 1 is less than or equal to x, and I also have the inequality of x is less than 7. The x is less than 7 graph seems to be a little easier for most of you guys because it's what you've seen. I'd come over here and I'd have an open dot, and I know I'm going to the left for less than. This first one is a little more difficult. 1 is less than or equal to x. Just like we've shown before with equations, you can flip the equations or flip the inequalities. But again, if I flip the values, I need to flip the sign. So to graph this other inequality, I will look for x is greater than or equal to 1. In that case, I would mark 1 with a closed dot, and greater than would be to the right. And now you see the very, very different look of the graph of compound inequalities here. Instead of an arrow going in either direction, we kind of have a closed set. Last example is probably the most difficult because it takes all the different things we've talked about in this video. To isolate the variable, we first would use the cover-up method and see that we need to add 1 on both sides of the inequality, and that means 3 different times for a compound inequality. This gives us negative 6 is less than or equal to a negative 2x, which is, of course, less than 4. To solve now for x, I'm looking at that middle value. I'm looking at the variable. To get it by itself, I need to divide by a negative 2 on every side. And so notice I have to do that 3 times with compound inequalities. Go back to the initial part of this lecture. Remember, every time I multiply or divide by a negative, I have to flip the arrows. This gives us 3 is greater than or equal to x, which is greater than negative 2. When it comes time to graph, I absolutely recommend that we separate this into 2 different inequalities to help you visualize this and help you go about graphing it. And again, if I have an issue with not really understanding how to read the whole idea of 3 is greater than or equal to x, I can always flip these, and when I do, I can flip the arrow. I see that x is going to be less than or equal to 3, and I want to graph that portion of this, and I also see that x is greater than negative 2, and I want to graph that. I'll start at the lower bound, which is negative 2. I see that it's greater than but not equal to, so I will use an open dot. I'll be heading over to the upper bound of 3, and now that I see that it's less than or equal to 3, I know I can use the closed dot. Now I just need to connect those. I have the greater than negative 2, and I have the less than 3, and I have my compound inequality graphed. Very, very quick look at examples of solving inequalities. Some important things to remember. Anytime we multiply or divide a side by a negative number, then we have to flip those inequality signs to make sure that they're still true. Other than that, I think it's a very basic use of your background knowledge and of your understanding of inequalities. If you have any questions, you can use the discussion board or we can discuss in class.